to. We'll start doing that. All right, number 13. Algebra. A golf ball is hit from point A to point B, which is on the ground as shown. Point A is 30 meters above the ground, and the horizontal distance from point A to point B is 300 meters. The path of the golf ball is modeled using this equation. The graph of this equation is drawn below or above. Oh, yep, sorry, below. So that's the situation. That's the real life situation. There's the actual graph of that equation. What is the maximum height the ball reaches above the ground? 40. There are two equations when the golf ball has had a height of 35. What horizontal distance does the ball travel in the period between these two equations? Okay, it's not asking you. It's not asking you to actually say the distance that each one is at. It's asking you to find out the horizontal distance between them. So that would be 100 and, what did you say? 40. That's 100, that's 200, that's 150. It's going up by 10. I got 120. No, am I wrong? That's 50, 100, 10, 20. I got 120. Let's double check it again. Is it 120 or not? Yep.
Thank you. Oh, she called me about
Can you give a buzz tomorrow? And I know we'll do 5:30 session on Monday as well. There's a possibility of that. Call me, please, tomorrow. 11, if you can. Anywhere from 11 onwards.
Okay, I have uni until 12:30.
So that's 12:30.
Okay.
Thanks.
No worries.
Do we agree with 120 then? No. 140. Maybe I'm wrong. So that's 100, that's 200. I think that's 150. 1, 2, 3, 4. Why are you guys saying 140? Sorry?
Where do you want 50 from?
The one you drove down is not on 135.
It's on 170.
Oh, that's why. How come I just started it from there? I don't know too. Thank you. Oh, are you serious? Okay, so it should have been from here. Which you're saying it's 140 now? Of course, because 20 there, 20 there. Okay, 140. Thank you. What is the height of the ball above the ground when it still has to travel a horizontal distance of 50 meters to hit the ground at point B? So if it still has to travel 50 meters, that would be there. So there. And what number is that? 15, 16, 17. What is the height of the ball? 17. Only part of the graph applies to this model. Find all values of D that are not suitable to use with this model. And explain why these values are not suitable. So what values of D are not suitable? Ooh, I like it. Because I think students would have only got 1 mark for this. But let's see, what did you guys write?
Anything below 0, anything above.
All right, then you get it. Damn it. All right, anything below 0. So that's anything here. And anything above 300. Anything after this. See, I knew there would be one person with the 1 mark. Christian, but it makes sense, right?
Yeah.
And then explain why these are not suitable, because you're not going to have negative distance for the first one, and the other one, it means you're going beyond the Earth's surface. Okay, this does make sense. All right, number 14. Last one. Wind turbines such as those shown are used to generate power. In theory, the power that could be generated by a wind turbine is modeled using the equation T equals 20,000 W cubed. T is the theoretical power generated. W is the speed of the wind. Okay, using this equation, what is the theoretical power generated when the wind speed is 7.3? Obviously, you'll just sub it in. Did we get an answer for this? 20,000 times 7.3 cubed?
7,700,000. It's just 7780.
7780.
340.
340 in watts. Any questions there? In practice, though, the actual power generated by a wind turbine is only 40% of the theoretical power. So it's only 60% efficient. Does that make sense? So 40% of it's gone. If A is the actual power generated, in watts, write an equation for A in terms of W. Well, didn't I just say A is 60% efficient? So then wouldn't A equal to 60% of T? Does that make sense? Because only 60% efficient. And obviously, what does T equal to? 20,000 W cubed. And then what's 60% of 20,000? 12. Someone's checking it for us. 12,000 W cubed. The graph shows both the theoretical power generated and the actual power generated. Theoretical and actual power. There it is. Theoreticals at the top, actuals at the bottom. Before I move on, any questions from I or double I? Okay. Writing it, Alyssa? All right. Just let me know. I'll explain to you in a second. Triple I. Using the graph or otherwise, find the difference between the theoretical power and the actual power generated when the wind speed is 9. Well, actual power is somewhere there. And theoretical power is 9, right? It said 9. 9 is somewhere there. 9 is there. So what's that? We've got 14 point, wait, that's going up by 1, 2, 3, 4, 5. So that's 2 divided by 5, 0.4. Okay, so that's 0.4, 14.4. My God, 14.4. It's because it's a link that we've copied in. 14.4, and this is 4.4, 4.8, 5.2, 5.6. Somewhere there would be 5.6. It's going up by 0.4. So obviously, what's the difference between 14.4 and 5.6? Give or take. You got to understand, for questions like that, when you're given the graph, there's always a 10% leeway. So if I went 5.7 by accident, it's okay. They're not going to deduct that many marks off you. If anything, there's only one mark. What's the answer? 8.8. 8.8?
Yeah.
A particular farm requires at least 4.4 million watts. 4.4 million watts of actual power in order to be self-sufficient. What is the minimum wind speed required for the farm to be self-sufficient? All right, 4.4 million. So I'd say this is going up by 0.4. So 4.4 million will be there. Which one do I read? Do I read the theoretical or the actual? What do we think?
Actual.
Yeah, I think actual as well, right? As if the farmer wants to know, in theory, you can do it in like 6 meters per second. What he really wants to know is, actually, you need it to be 8.2. 2, 4, 6, 8. The bottom one's going up by 0.2. 8.2. Not letting me write a dot. Serious? 8.2. All right. So therefore, what is the minimum wind speed? Yeah, we said 8.2. meters per second. A more accurate formula to calculate power is this. P equals 0.61 times pi times r squared times w cubed. R is the length, W is the speed. Each blade of a particular wind turbine has a length of 43 meters. So now we know that R equals 43. The turbine operates a wind speed of 8. We know W equals to 8. Using the formula above, if the wind speed increased by 10%, what would be the percentage increase in the power generated by this wind turbine? All right. So if it increased by firstly, you've got to work out what is it right now. So step 1. I'll just do it down here. Right now, P equals 0.61 times pi times R squared times W cubed. Thank you. What does that give us? 0.61 times pi times 43 squared times 8 cubed. 1814205.92. Now, and then I will write then, or after, let's write after 10% increase in W. So if W increased by 10%, what would W be? My new W would equal to 8 times, an increase of 10% is 1.1, right? You got to increase it by 10%. So 8 times 1.1 is 8.8. So if wind speed was 8.8, what would be my power? Well, write the whole equation again. 0.61 times pi times 43 squared times, instead of 8, you're going to write 8.8 cubed. Plug it all into your calculator. Two, 4, 14708.08. Question says, if the wind speed increased by 10%, we just did, what would be the percentage increase in the power generated by this? So how much did it actually increase by? How do we work out percentage increases? Does anyone remember the formula for working out how to find percentages? Increase or decrease? I usually label it as new. It's very close, Christian. New minus old over old times 100. You're very, very close. So what's the new? I'm just going to call this new. We'll call this old. I'm going to plug it into my calculator. Let's see what it gives us. Minus 1814205.92 over 1814205.92 times 100. It's actually a 33% increase. If wind just improved by 10%, you've actually improved the whole thing, the whole power output by 33%. That's huge. All right, I'll pause there.